All right, guys, in this lesson we're going to review how to solve three types of equations. Log equations, which you guys can see we're doing here on numbers 1 through 12. And we're also going to talk about how to solve, let's see if I can scroll down here, exponential functions. That's numbers 13 through 18. And we'll also review how to solve rational functions at the end, 19 through 24. So let's go ahead and begin. How this one's going to be set up is I'm going to have you guys do number one. I'm going to do number 1, and then you guys will do number 2. And we won't have notes and practice separated. We're just going to call the practice part of the notes here. So let's go ahead and have you guys begin. Take good notes as we go. So this is a log equation. The main step to solve a log equation is to exponentiate. Okay, so what does that mean? When you have a log equation, you have a log. It's going to have some kind of a base. We'll call it b. The x will be here, and then there'll be some number over here. We'll just call it c. Okay? To exponentiate, what you do is you make both sides a power of your base. So my base is b. So I make this a power of b, and I make this a power of b, and we get this. Now, the reason that we do that is because there's a log property that tells us when you have an exponential expression where this number matches the base of the log, these cancel each other out, and you're left with x by itself. So that's the goal there. All right, so let's go ahead and put that to practice here. I'm going to exponentiate both sides using what number? 5. All right, now this cancels this, and I'm left with x equals 5 to the third, and therefore x must be equal to 125. All right, so that's our first example there. Have you guys go ahead and write down number 2 and go ahead and do that. If you want to pause the video here and do it, you can. We're going to move on to number 3. This is another example, and there'll be a practice problem after it. All right, let's go ahead and take a look at number 3. Now, number 3 is another type of log equation. This one has extra stuff on the inside. It actually won't change our first step at all, though. I'm still going to exponentiate both sides. I'm still going to cancel these out and get left with this. 6 to the 4th power is a pretty big number, so I'm going to use my calculator for that. 6 to the power of 4 is 1,296. And then from there, I'm just going to go ahead and solve for x. So that's the only difference, is at the very end, you just have a little bit more basic algebra to do to get the x by itself. You could probably just leave it as a fraction. Just make sure you reduce it if you do. Or you can change it into a decimal. It doesn't really matter. All right, so here's one for that example. I'll let you guys go ahead and do that, and we'll move on to our third example, number 5. Now, whenever you have extra numbers outside the log, so here's my log, but I've got these extra numbers outside of the log. So we want to get rid of numbers outside the log before we solve. Or I should say before we exponentiate. Okay, so let's do that. The first thing I'm going to do is I'm going to minus this 4 on both sides. And then I'm going to divide the 9. Okay. After you do that, after you get rid of the numbers outside of the logarithmic part, you are going to just go ahead and do it like we did the last two problems, which is by exponentiation. So the base is 6, so that's what I'll be exponentiating with here. These cancel out. In case you guys forgot, 6 to the negative 1 power is 1/6. A negative power just causes your number to go to the bottom, and then after that the power becomes positive. So 6 to the negative 1 power is 1 over 6 to the 1 power. All right. From there, we're just going to go ahead and solve this. I don't like fractions, so the first thing I would do to solve this is I would multiply everything by 6. So if I multiply that by 6, I get 1. If I multiply this by 6, I get 36. And if I multiply that by 6, I get negative 36x. And then from there, simple algebra stuff, minus the 36 on both sides, and then divide by negative 36. Since they're both negative, we can cancel the negative out, and there's our answer. Okay, so here's number 6 for you. That one also has some outside numbers for you guys to get rid of, and I'll leave that one for you guys to do. Number 7. This is another type of log equation. Nothing special really happens here. We're just going to exponentiate both sides. There's no numbers outside of any logarithms. So we could just start with exponentiation once again. But what is interesting here is that since there's a log on both sides, the log cancels on both sides, like so, and we're left with this. That's supposed to be an equal sign. All right, and then we just solve. So I'm going to start by adding 4p on both sides. And then I'm going to minus 7. And then I'm going to divide by 9. And so I end up with p equals negative 1/9. Now, what is important about these types we need to make sure our answer is not extraneous. And what do I mean by that? Well, sometimes when you're solving log equations of this sort, the answer you get may not be allowed, and the way you can tell is by plugging it in. The part inside the log has to be positive. Okay, so here's what I mean by that. It doesn't mean your answer has to be positive. It means that after you plug your answer in, you should have only positives inside of the logarithm. So for instance, if I have a log of 12 and I were to plug in negative 1/9, for p, I shouldn't have any negatives on the inside after I simplify this. So for instance, if I multiply these together, I get 6 plus 4/9. Now, you can add those and get a common denominator if you want to, but you can already tell that this is not going to be a negative number. So this is a good thing. But we have to make sure it works on the other one also. So let's do that. This is negative 5/9. If I add these by getting a common denominator, I would have 63 take away 5, which is 58 over 9. That's also positive, which is good, and therefore we have a good solution. All right. But if you plugged in negative 1/9 and these things came out negative in the end, then we would have to throw the answer away and call it extraneous. All right. So I'll give one for you guys like that here. I'm going to move on to, there's yours, and we'll move on to number 9. This is another log equation, but this one has ln in it. So just to kind of remind you guys how to deal with ln, it'd be nice if this had parentheses on it, because it's not saying ln minus 10n. It's ln of negative 10n. So we do have outside numbers here, so the first thing that we would do is we would divide both sides by a -5 to get rid of the outside numbers. We talked about that back on number, I forget, our third example anyway. You always start by getting rid of the numbers that are outside of the log. Next, we want to exponentiate. And this is where the special note comes in for this one. For ln, we exponentiate with e. Okay, so this is going to be e to the ln of negative 10n and e to the -1. And these cancel out, and I've got negative 10n. E to the -1 is 1 over e. And then I just need to divide both sides by 10. And I'll just put the 10 on the bottom over here. And so we end up with 1 over 10e. And you could just leave your answer like that. In case you guys forgot, this is just a little side note, but e is approximately equal to 2.71. It's just a number, it's not a variable, but we leave it as a letter, even though it does represent a number. It's a lot like pi in that way. All right, so here's one for you guys. Go ahead and try number 10, and we'll move on to number 11. This is a similar situation. Let's go ahead and begin by getting rid of the outside numbers here. The 10 needs to go away. Now, in this case, if the log is missing, if the base is missing, we exponentiate with 10. Because on a log where they don't actually write the base in, the base is 10. And so we would exponentiate with 10. And so these cancel out, and we're left with p minus 8 equals 100. Go ahead and add 8 on both sides, and you get p equals 108. Okay, so just two special types of logarithms to be aware of there. Here's one for you with a base of 10. And we'll go ahead and move on to a new type of problem. We're talking about exponential functions. So, to solve exponential problems, we log both sides. Now, whatever base you use on your log, it depends on whatever base you have for your exponent. So, for instance, if you have base b to the x equals c, then what you would do is you would log both sides with a base of b on both sides of the equation. So basically just put a log base b on both sides. And we have a log property that tells us that these cancel out, and that gets x by itself. Okay. Now for these problems, we're also going to need to use the change of base. Which requires the use of a calculator. The change of base, in case you forgot, which you probably have because it's been a while, tells me that I can change this base b to anything I want. Now in a calculator, we want base 10. There's also base e, which is ln. You could use that one also. But just to kind of keep things simple, we'll do base 10. So log base 10 of c, log base 10 of b is the same thing as this. So you just rewrite it using that formula. So we're going to be using those two strategies here on this problem. So to begin, let's solve this. First of all, I'm going to log both sides. And when I log both sides, what base will I use? We're going to use a base of 6. So I just put a log on both sides with a base of 6. All right. Next, we use our log property, and these cancel out, and I've got b by itself. And so here's my answer, log base 6 of 87. Now, you could technically leave your answer that way, but we're going to be transforming these into decimal answers, and to do that, we're going to use our change of base. So I'm going to use log base 10 on the top and bottom of a fraction. This number goes on the top, and this number goes on the bottom. And from here, you're just going to type that into your calculator to get your final answer. So let's go ahead and do that. I'm going to do log 87 divided by log of 6, and I get 2.492. It's good to maybe round to at least the thousandth place. Log and exponential functions are pretty sensitive, so you want to be precise as possible. I think going to the thousandth place is probably good. So we did two things. We logged both sides using that, and then we used our calculator along with change of base to change our final answer into a decimal. All right, so we'll let you guys go ahead and try one of those. There's one for you, and we'll move on to number 15. Now, here is my exponential expression here. We want to get rid of the outside numbers again before we begin. Get rid of outside numbers before logging. Okay. All right, so we have negative 5 e to the m minus 5 equals negative 54.4. I want to get this piece by itself, so I want to get rid of the two negative 5s. The first thing I'm going to do is add 5 on both sides. So what is negative 54.4 plus 5? That's going to be negative 49.4. Next, I'm going to divide both sides by negative 5. And let's see what I get. Using my calculator once again, I get 9.88. After you've gotten rid of your outside numbers, it's like all the other ones. Now, my base here is a base of e. So when you do that, we're going to log base e. And what that means is we're going to use ln to log it. So we have e to the m equals 9.88. I'm going to log both sides with an ln. And we do that to cancel out the e, which leaves me with m. Now, you don't need to use change of base for this one, because we have that button on our calculator. ln of 9.88. I've got an ln button. So I'm just going to push ln of 9.88, and I get 2.290. Now, on your sample problem that I'm going to bring up for you guys here, it's not going to be in a base of e. It's going to be a base of 2. So for this one, you will need to use the change of base. So I didn't have to use that on my problem. You will, okay, because yours is not a base of e, it's a base of 2. All right, let's go ahead and move on to another one. So let's find our exponential part. My exponential part is this guy. I've got 7 to a power there. Everything else is what I call an outside number. So I'm going to start by adding 8.2 to both sides. And negative 66 plus 8.2 is negative 57.8. Now I need to get rid of the negative 2, so I'm going to divide both sides by negative 2. And that's going to give me on the right side 28.9. And now, at this point, we're going to log both sides. What base will I use? 7. Oops. Now on the left side, these cancel out, and I'm left with 7.5 minus 7x is equal to this. On the right side, though, we're going to need to do the change of base. I'll abbreviate that COB. So that's going to be 7.5 minus 7x is equal to log of 28.9 over log of 7. And let's see what that is. Once again, I'm going to have to use my calculator for that. So log of 28.9 divided by log of 7 gives me 1.729 approximately. And then I'm going to minus the 7.5 on both sides. And from here, we're just solving for x. And I'm getting 0.824. All right. So there's one of those for you guys. I'll let you guys do number 18. And now we're going to transition into our third type of equation to be solving today, which is rational expressions. All right. For rational expressions, what you want to do is you want to get rid of the denominator by multiplication. So that's our main goal there, is to get rid of the denominator by multiplication. Now, what do you multiply by? You want to multiply by the, what is it called? The common denominator. So this one has an a squared, this one has an a squared, this one has an a. So what's the common denominator for all those? It would be a squared. Okay? A needs a little bit more, right? So we're going to multiply everything by the common denominator a squared. So I'm going to multiply that, and when you do that, you just put it on the top of every fraction. And so I'm going to end up with a squared over a squared plus 2a cubed plus 10a squared. Actually, let me back up a little bit. I don't like how I wrote that. Just put it on the top. Don't actually multiply it. I'll show you why in a second. And we could put a 1 here because there was 1s to begin with. So if you just put an a on the top of every fraction, that's what you get. Since I changed the way I did that, I'm going to rewrite my arrows. So you just put 1 here, you put 1 here, and you put 1 over there also. Okay, so there's that. Now, these cancel, and I'm left with 1. These cancel, and I'm left with 2a plus 10. And these cancel, and I'm left with 1. So that's the trick there, is to multiply by the common denominator. After that, you pretty much have a pretty simple equation to solve. So you have that. We can combine the 1 and the 10 together to get 11. And there you go. All right, so the main trick with solving rational expressions is to multiply by the common denominator. All right, so let's go ahead and move on to number 20. So you guys would have to think about what is your common denominator here. I'll move on to number 21. All right, so when you have polynomials in the denominator, you have to begin by factoring. So there's our main note that we're going to write there. And you only need to factor the denominator, okay? So for this one, you can't factor v minus 1, so I'm just going to leave that alone. This one here, there's a greatest common factor, so I could take a v out of there. And this one over here has the same thing, so I could take a v out of the denominator there as well. Okay, then after that, you're going to multiply by the common denominator. So this one has a v minus 1. This one has a v minus 1, but it also has a v, and so does this one. So my common denominator that I want to multiply by is by v and v minus 1. And we're going to put that on the top of every fraction here. And just so you guys know, anytime you're working with rational expressions, it's a good idea to put parentheses around your binomials. It kind of helps in the case where you need to distribute or something like that. If you don't have those parentheses, you might forget to distribute. Okay, so let's go ahead and put that in there. If I were to put v times v minus 1 on the top of every fraction, it would look like this. Okay, and then after that, we're going to go ahead and start reducing whatever we can. So like this goes away. The v's go away here, and the v minus 1s. Same thing over here. And now I have a little bit of a simpler equation. I've got 1v, so I'll just write v, and then 3v minus 18, and then v plus 4. Now this is where it's kind of important that you have those parentheses like I told you, because you might not have realized you need to distribute this negative if you didn't have those parentheses there. So we have v equals 3v minus 18 minus v minus 4. After you distribute, then you can get rid of the parentheses. So let's go ahead and combine our terms together here. I've got v equals 3v and minus v is 2v. Negative 18 and negative 4 is negative 22. I'm going to move this 2v to the other side. You can think of that as a 1. 1 minus 2 is negative 1v. And then I would just divide both sides by a negative 1. There you go. All right, so the main thing to focus on here is that when you have polynomials, not just like a single term, but a polynomial in the denominator, you have to begin by factoring it so that you can find the common denominator, which is what you multiply by. And so you'll have one like that. This one actually is not polynomial, so this one's going to be a lot more like the last one you did. Here is another one. We'll do another one. So once again, I've got polynomials in the denominator. So the first thing that we're going to do on this problem is we're going to begin by factoring that denominator out. I can take a 3 out there. For the next one, I can take a 3 and a k out. Same thing with this one. So now I'm going to multiply by my least common denominator, which is 3. They all have a 3. K, because some of them have a k, and also k minus 5. So we're going to multiply everything by 3, k, and k minus 5. Okay, and we're going to be putting that on the top of each fraction. Okay, and so here we have the 3's canceling, and we have the k minus 5's canceling. Leave me with a 4k and a k, which makes 4k squared. Then for the next one, we have the 3 and the k canceling. Then the k minus 5, leave me with just 2. And over here, all three of these cancel all those out, and I'm left with 4k squared plus 4k minus 48. Now, the next thing we'll do is we'll start combining our like terms. Now, a little note that I'll put here is if you have a squared term, like here we've got a squared term, you may need to use either factoring or quadratic formula. I'm going to go with factoring to solve. Okay, and so when you have a quadratic, the first thing you want to do is move everything to one side. So I'm going to subtract the 2 on both sides there. Then I'm going to put the k squares together. Now, on mine here, I'm going to end up with a unique situation. I'm going to have 0, and now these cancel. And so mine becomes pretty easy to solve at this point because I don't have any more squared terms. But I do want you guys to know that if your squares don't cancel, the way you're going to solve it is by factoring and setting each piece equal to 0. Okay? But for me, I don't have to do that. I'm telling you this because I think it's going to be like that on your student practice that's coming up. So for me, it's pretty simple. I just get this, which reduces to that. But for you guys, I'm pretty sure with your practice problem I'm going to give you, it's going to require you to factor a polynomial. So there's one that matches that for you guys. And that'll be it for today. So hopefully that was helpful. We'll see you guys later.